Rubik's Cube is a very fascinating piece of a puzzle. My nephew introduced me to them, well, a long time ago, but I never really got around to actually solving them until recently. So, when I was studying abstract algebra, um, I came across groups, and I discussed what groups are in my Professor Femi video. They're not necessarily collections of things, that's a set, but rather a specific type of set. And there's a type of group called a Rubik's Cube group. And a Rubik's Cube group is basically just the structure of the puzzle itself. So, given a Rubik's Cube with which is 3 by 3 by 3, so we have three facets with 6 sides. The Rubik's Cube's group has a cardinality or size of 33 4325200327448985600. So 43 and 2, 3, 4, 5, 6 sextillion 252 quintillion 3 quintillion 274 trillion 7 billions 274 trillion 489,856,000 moves, which is also expressed as 12 factorial times 20 to the 2 to the 20 times 8 factorial times 3 to the 7 possible moves. And so what's the structure of this group? So if we have the Rubik's Cube group G, what are the elements of G? So the elements of G are the possible moves we can do on the cube. So suppose what we cubers usually do is, or what I'm taught at least, is that we keep the white side down and you can use any face. So I'm gonna use the blue face, let's say. So actually this cube is my nephew's. I'm borrowing it while I'm studying how to solve it. I think I got it down to around 4-6 minutes for my solving time. I'm gonna learn speed cubing tricks and all that. But I generally got the gist on how to solve it. And it's not really by face but by a layer. So okay. Going back to the problem. The Rubik's Cube puzzle is really composed of the moves that we do. So this group that we have of the possible moves are the moves that we can do, or the Rubik's Cube group is basically the moves, or a group composed with an underlying set composed of the moves we can do on a Rubik's Cube. So assume we have a 3 by 3 by 3 Rubik's Cube with 9 facets on each side, such that the central facet does not change. So if we take apart the structure, as you may notice, this thing only rotates, it doesn't really move to another side. But these facets can, as you can see. So the first move, and actually it's actually really nice that mathematicians who made the Rubik's Cube group also used Rubik's Cube notation. Or maybe it was the other way around, wherein cubers actually started using the math notation for this. So assume this face that's facing you is the front. This part that's facing away from you is the back. This is the up. This is down. This is right. This is left. Of course, common sense. So the first one that I like to start with is F, and that is turning the front face 90 degrees. 90 degrees. And F prime is doing the opposite, putting it back. Or if we're in the starting position or the solve position, this is called the solve position, turning it counterclockwise. That's F prime. I actually want to use F and F to the -1, but it would be tedious to say F to the -1 R, especially when you're composing them and trying to describe an algorithm. And so yeah, the next one, I'm going to discuss about algorithms once I'm done discussing this. So F2 or F2 or F squared is basically turning it 108 degrees clockwise. So turning it like this and then turning it again. But the thing is, when cubers usually communicate notation or algorithms to each other, they don't really use F too much. It's mostly done for advanced algorithms. But for the basic type of algorithms which I'm interested in, we'll mostly use these guys. So just the original ones and their primes and their compositions. Okay, so the second one is, I'm gonna go with down. So actually back. Back is turning the back face clockwise. So keeping in mind this is the front, let's turn to the back and turn it clockwise. And then the same thing for like that. And then just like same thing for prime, B prime, B prime. So there's F prime, B prime. But I don't think they use B much. It's mostly F, U, D, and R, and L. So the next thing we're gonna discuss is R, which is well, of course, right. This layer here. So this side here, we're gonna rotate that clockwise. That's R, R prime, R prime. This is L. This is the same thing. L, L prime, L prime. And then the same thing for up. U prime, U prime. And down, it's a bit this. D prime, D prime. D prime. And yeah, that's actually all the moves we can perform on this. So as you may notice, each of these moves can actually be a cyclic group. So if we were to compose a cyclic group of just this, we can just doing this on the cube, we can already form a group out of that. So that would be a cyclic group wherein all of these guys would actually be, they would extend onto infinity. But things such as F cubed, applying it thrice, 1, 2, 3, 1, 2, 3, 4, would actually be just the same as doing nothing. So it would actually, most of the terms in this cyclic group would actually cancel out. And so actually the real group is the symmetric group. So the group that's composed of these moves, F, B, U, D, L, R, is actually a subgroup of something called a symmetric group. And a symmetric group basically just tells us the various symmetries of the object. So if we rotate the Rubik's Cube, assuming that there's no colors, right? Or colors is not an important property, right? Rotating the cube such that it looks exactly the same after the rotation is a symmetric move. And the line that we rotate around, or the axis that we rotate around, is called the symmetry. And the Rubik's Cube group is actually a subgroup, or a subset, or just a part of the S48 subgroup, or symmetric group. So the symmetric group S48. It's just a subpart. It's just a part of it. Now, you can think of this as actually the free group on this set. So this FBUDLR, the cardinality of the group of the Rubik's Cube group, or the actual Rubik's Cube group, is the free group over this one over here with the composition. Now let's talk about composition. When we think about composition, we usually say, okay, we usually start with functions, right? So applying a function on one number and then applying a function on that function. So when we think of composition, usually think of going from right to left. So f of g of x. This is a composition, which is denoted by this circle. But in abstract algebra, we actually do it like this. We just write it next to each other, or we use the dot operation. But we must note that when we put two functions together or two elements together, they do not necessarily mean that we're composing them or performing one after the other. It could be a placeholder for any operation. Like when we think about magmas and sets that have a closed operation, so it's closed under a certain operation such that two elements, the result of applying an operation on an element is still inside the set. That's closure. This does not necessarily mean that we're multiplying them or we're composing them. So now, speaking of composition, when we compose elements of a group, it's basically doing one element and the other. So if we think of each element as an action on the cube, like say, I want to perform R, and then I want to perform U, we get this phase. Now, the thing about this kind of group, the Rubik's Cube group, is that it is non-abelian or abelian. I like pronouncing it as abelian, but people also pronounce it as abelian. So when we say that a group is non-abelian, that means when we compose two elements, order matters. So when we say it's a non-abelian group, it is also called a non-commutative group. And so any moves that we perform on the cube is non-commutative. What I mean by that is that, okay, I'm gonna write down the action here. So I'm gonna do R U. And I'm gonna state it is not explicitly the same as U R. Because notice, R U. Okay, we get this red here and these two white. I'm gonna put it back. This time I'm gonna perform up first. So up R. This is different now. This time it's red here and yellow here. So since it's different and it gives us different colors, it's not the same thing. It's not the same algorithm. And so strings or clean star operation, the clean star operation we can perform on this set is actually n here, or is the underlying set of the Rubik's Cube group. Now the clean star operation, which we denote by, let's say, K. We have a set K, and we want to perform a clean star operation on K. The clean star operation here, or K star, is the set of all words we can form out of the elements of K. So when we say word, we basically put them together, the finite combinations of these guys. So let's say that K is composed of just up and down moves. The clean star on K is the set, it's not really subsets, but rather elements. UD, DU, U, and D. Note that if we have a set, it doesn't repeat. We don't repeat elements. Yeah, we don't care if it repeats. It's basically the same thing. It's like saying, well, you have yourself in there, right? So UD, DU, UD. This is the clean star operation we can do on K. So suppose our Rubik's Cube group R is composed of, I'm gonna make it a bold R so you don't confuse it with the right move. It's composed of U, D, L, R, F, and B. As you notice, when we take the clean star operation of R, it would be actually very big. It would be, first we have to go with U, D, L, R, F, B, and then U, D, or actually U, 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 D, 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 and stuff like that. It's almost infinite because there's a lot of combinations. In fact, the amount of combinations, as I said in my notes, is precisely 4325200327448985600. That's the amount of combinations we can make, and it's impossible for us to write that out within my lifetime. So, yeah, all the possible combinations. And the thing is, with the clean star operation, unlike free groups here, which we mean an arbitrary number, so it can be finite and infinite. When we say clean star operation on this set, we're talking about finite words. So not necessarily finite sequences like u, dot, dot, dot. It has to be something like u, and then stop. Next, u, stop. And then u, stop. And then eventually after that, we get D, 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 and then dot, dot, dot. And then L, and you guys get it. Now, the math the philosophical thing behind this is that when we assume that this set is well ordered, when we assume that this set R is well ordered, or this clean star operation of R is well ordered, okay, U dot 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 D dot 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 L dot dot dot, and I'll just close it there. If we assume that this set is well ordered, we can use the well ordering theorem, which basically means that in a well ordered set, any element has an immediate successor. So that means we can count beyond infinity with this. So since when we start with U, we already start to get an infinite number of U sequences. U, 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 and then, you know, you guys get that. So this is our first infinity over here. And according to the well-ordering theorem, if we treat this first infinity as an object in itself, or an element itself, omega, then there is a second infinity after that. So actually, to better encompass it, let's call this entire set omega. This entire infinity. So there's infinity here, and then this next infinity, and this next infinity, and then the combinations. Let's assume that's an infinity. There is a second infinity beyond omega, which is composed of this set again, which, well, obviously is 2 omega. And then, you know, we can do that 3 omega, 4 omega, dot dot dot, until we reach omega to the omega. And then omega to the omega, omega to the 2 omega, omega to the 3 omega, omega to the 4 omega, and then, you know, you guys get it. And then eventually, it'll reach big omega. And big omega is just sort of, it's sort of where things start get blurry, and that's where the theorem actually starts to contradict itself. Because since it's well ordered, when we say that a set is also well ordered, the set almost have finite subsets. So it must stop at some point. So every subset has an upper bound. So when we say here U's upper bound is D. It stops at D, right? And then, you know, eventually this omega stops at 2 omega and stuff like that. But the thing is, when we continue applying the well-ordering theorem to this well-ordered set, because this has immediate successors, it's immediately a well-ordered set, we immediately start seeing that this entire set has no bound. It has no bound. And, well, we can say that a set is a subset of itself. This makes sense. This is perfect sense. And when we say that this is not well ordered, because, you know, this subset itself, this section, we call section of omega, does not have an upper bound because it keeps going, then we're saying that A is not a subset of itself. So A is not well ordered here, which means this is not well ordered. Because for a well ordered set to be a well ordered set, its subsets must be well ordered as well, which means that they need to have an upper bound. But the thing is, we don't have an upper bound, so it's not well ordered, and it's not well ordered. But we asserted in the first place that it is well ordered because they do have immediate successors. So that's where the sort of theory the theorem starts blurring. So what we do is define a limit. We stop it at S omega, which is just our upper bound, but it also tells us that this is a subset of the entire omega, which is it keeps going on and on. And that's to prevent contradictions. And so that was actually a brief tour into topology and, you know, sets and stuff like that, and actually abstract algebra. This is where I first this is where my interest kicked off for the Rubik's Cube. Before I learned about the Rubik's Cube group, I actually didn't have much interest in this thing and in solving it. But now that I actually studied the math behind it and sort of, you know, got a feel for the algorithms and stuff, well, I pretty much enjoy solving it, even though there are times where I feel a bit frustrated and I have to repeat things. It's part of the fun, to be honest. And I suggest you guys try these things out for yourself. Whether you're on the CR taking a dump and you need to do something that's not on your phone, try solving a Rubik's Cube. There are tons of videos online that can help you solve this thing. But there's a 10-minute video by J Perm that really helped me do this. And of course, my nephew helped me. He's a wonderful guy. He's only 2 years younger than me, but he's a really smart guy. So I'll link the video of J Perm down in the description below. Huge shout out to him. Great job, and really appreciate his help. Now let's talk about algorithms. Now, the algorithms here, when we talk about the Rubik's Cube and Rubik's Cube puzzles, it's not the algorithm that we think about in math. No, it's not. It's not like something like the Newton-Raphson method. It's not like that. It's not like Euler's method. But the premise of using it again and again until you eventually achieve what you need, those are what these things share in common. So like how Newton's method is applied again and again to approximate roots of a polynomial, and how Euler's method is applied again and again to approximate a function or the numerical value of a function given some boundary conditions. Algorithms, when it comes to solving the Rubik's Cube, is something we apply again and again until we achieve a desired state such that we can start applying it and then get a step closer to solving the cube. So the first thing that we actually do is the white cross. And there are algorithms that we do or we memorize to get the stuff in place. And if you scramble your Rubik's Cube for the first time and you feel frustrated, you feel like, oh, it's so complicated. I can't solve it. It's so hard. It's really about thinking about these guys and actually the central pieces, breaking down the Rubik's Cube into its components. This is the centerpiece. Ignore for now. These are the corner pieces. Ignore them as well. When you're making your first move and taking the white cross or trying to solve the white cross, you guys need to memorize. This algorithm is actually very helpful, and it's F U prime. R U prime. So this switches these two guys, and so we get this part of the cross. And really, it's about memorizing algorithms. And I know it's a bit unintuitive, but if you guys keep practicing, you guys are gonna get this. So we're gonna look for edge pieces and try to line them up with their respective colors. So this white here, we're gonna line up the blue and then up. So this part here is formed. And so next thing is red. So this is red. We're gonna try to bring it over to the red side. So there, like this, and then flip it around like that, and like that, and we have to apply that algorithm again. There. So this T is done. The last one. This time we have an orange, and now we're gonna try to bring it down, bring it to the orange centerpiece. So you may need to move it a bit, and then return that white, and then rotate. And if it's your luck, you get to do it fast, and you don't need to worry about these guys being switched. So that's just a small taste of solving a Rubik's Cube. It's really about analysis, and this is why I'm fascinated by it. It's because it's like math. In math, we are given a problem. We're given a scrambled Rubik's Cube, and we're told to solve it. And so instead of thinking about the whole, the faces, I need to find out how to make the faces move, we break it down to the simple parts. How do we start solving the cross? We break it down step by step. If it's hard, break it down. Break down the problem. This is something that Blue Brown and many other mathematicians love doing when they begin solving a problem and it seems very hard for them. Break it down. So the first thing is cross. That's the first thing we do. And so that's the first thing we focus on. And that's honestly a really beautiful reflection of the Rubik's Cube and mathematics itself. When we begin studying abstract algebra, it may all seem very unintuitive and very, very complicated. Groups, fields, categories, monoids, magma. I don't know where to start. But it's best to start at the simplest concept, which is the set. And really, I'm surprised by how this video came out. This is actually done on the fly, and I'm amazed at how I made this connection. So it's actually beautiful. The Rubik's Cube is a perfect representation of how, or when you solve a Rubik's Cube, it's a perfect representation of how mathematicians think in terms of solving problems in mathematics. And yeah, that's it for this video, and thank you for watching. So yeah, I'm still in the middle of making my paper, so this is just one video I wanted to make in the middle of things. This actually helps in my studies. It's making my brain kind of sharp. It will make your brain sharp too if you try it out. Again, I'm gonna link the video, the J Perm's video below. Get yourself a Rubik's Cube or a speed cube like this. I like the speed cubes because I get to solve them faster. And yeah, I love the surprise connection it made with how I and other mathematicians, or well, problem solvers, solve math problems that seem difficult at first. So yeah, working on the paper, there's a bunch of new stuff that I've added. I think what's included is that the only thing I haven't included yet is this. Assuming that the set of all characteristics, or the universal set of characteristics, is well, it's like the natural numbers, or it's like omega as we see here, and then we can extend it on and on. I haven't included that in the paper yet, but I suggest you guys check out the paper down below. It may need some background knowledge on math, but you guys can search up the concepts and equally understand them. And ultimately, if you guys feel overwhelmed by the paper, start at the beginning, set theory. Start with sets. Start with that, and then build your knowledge from there on out. And that's really one of the important keystones of studying on your own. So this is where I'm gonna close the video. Thank you all for watching. Please subscribe. Your subscribing really means a lot to me. It really means a lot. And I know it may not pay the bills for my family, or it may not benefit me materially, but I feel genuinely happy making these videos for you guys. So I hope you guys enjoyed this video. Leave a like down below, and please share this video with your friends, and also my channel. You guys know the drill when it comes to YouTube. If you like what you see, do those things. Leave a comment down below. If you have any concerns, I'll be willing to put that in the description of the video in case I have said or done something wrong in this video. So anyways, that's it for today. See ya.